Good morning, everyone. I am LOHIT.S from the Department of CSE first year. Today, I am going to present the topic volume of a sphere using triple integrals. In this topic, we use calculus to find the volume of a three-dimensional object. Instead of using only basic geometry formulas, we apply triple integrals which allow us to calculate volume by integrating over a region in space. This presentation gives a conceptual overview of how calculus and geometry are connected. First, let us clearly understand what is a sphere is. The definition of a sphere is defined as the set of all points that are equidistant from a fixed point called the center. The constant distance from the center to any point on the surface is known as the radius r. It is denoted with small r. A sphere is a perfect three-dimensional shape, meaning it looks the same from every direction. Because of this perfect symmetry, special coordinate systems are useful, very useful. So now let us look at the different coordinate systems. To represent points in three-dimensional space, we use coordinate systems. The three commonly used systems are Cartesian coordinates, cylindrical coordinates, spherical coordinates. Each coordinate system is useful for different types of problems. Choosing the right system makes calculations easier. Now, let us understand why triple integrals are required. The triple integrals are mainly used for finding volumes of 3D objects. They work very well when dealing with symmetrical shapes like spheres. Triple integrals are also fundamental in engineering and mathematics, especially in physics, mechanics, and fluid flow problems. Since a sphere is a three-dimensional region, triple integrals are the correct mathematical tool. Now, let us see the basic volume representation. In calculus, volume is represented as V is equals to triple integral dV. This means we integrate a small volume element over the entire region. For a sphere, we integrate over the region bounded by the sphere's surface. To define this region properly, we must know the equation of a sphere. The sphere equation goes like the equation of a sphere with radius small r and center at the origin is x square plus y square plus z square is equals to r square. This equation defines the boundary of the sphere. It is symmetric in all directions, which makes spherical coordinates suitable. Let us now examine how this problem looks in Cartesian coordinates. Cartesian approach. In Cartesian coordinates, we integrate the respect to x, y, and z. However, the limits of integration become very complicated. The integration is hard and lengthy, so this method is not preferred for spheres. Due to this difficulty, we try another coordinate systems. So now let us move to the cylindrical approach. Cylindrical approach. Cylindrical coordinates are easier than Cartesian coordinates. They use radial distance, angle, and height. However, for a sphere, the limits are still complex, especially for the height variable. Cylindrical coordinates need radial symmetry, but they are still not ideal. So finally, we move to the best option, spherical coordinates. Spherical coordinates are the best choice for solving this problem. They provide simple limits of integration. Most importantly, they match the symmetry of the sphere perfectly, making calculations much easier. Now, let us understand the variables used in spherical coordinates. In spherical coordinates, we use three main variables: rho, distance from the region; theta, angle in the xy plane; phi, angle measured from the z-axis. These variables helps us represent any point inside the sphere easily. Next, we define the volume element in spherical coordinates. It is nothing but Jacobian in spherical coordinates. The volume in spherical coordinates is given by dV is equals to rho square sine phi d rho d phi d theta. This expression accounts for distortion when converting from Cartesian to spherical coordinates. It is required for triple integrals to correctly calculate volume. Now we decide the limits of integration. For integration, setting limits for a sphere of radius r, the limits are phi varies from 0 to r, sigma varies from 0 to pi, theta varies from 0 to 2 pi. These limits cover the entire volume of the sphere. Now let us set up the triple integral. Triple integral setup. The volume of the sphere is given by V is equals to integral 0 to pi, integral 0 to pi, integral 0 to t phi square sine phi d theta. This is a direct substitution using spherical coordinates. It follows a standard procedure for volume calculation. Now we evaluate the triple integrals step by step. Solving inner integral. First, we integrate with respect to phi. Integral 0 to r whole square d is equals to r cube by 3. This result is then substituted into the next step. It simplifies the expression significantly. Now, let us solve the middle integral. We integrate with respect to phi. This is a key trigonometric integral. It gives a constant result, making calculations easier. Now we evaluate the final integral, outer integral. Finally, we integrate with respect to theta. Integral 0 to 2 pi d theta is equals to 2 pi. This is the final multiplication step. With this, the evaluation is complete. Now, we combine all results. Final volume expression. Combining all results. V is equals to r cube by 3 into 2 into 2 pi. Simplifying the result, V is equals to 4 by 3 pi r cube. This is the required volume of a sphere. Now, let us interpret this result. This result matches the known formula for the volume of a sphere. It shows the triple integral validate geometric formulas. This demonstrates how calculus is a powerful mathematical tool. Now, let us see where this is applied. The applications of volume of a sphere is used in many fields such as in engineering and next in physics, in computer graphics, etc. These applications involve real-world spherical objects and simulations. Now, let us see a numerical example. Consider a sphere with radius 5 units using the formula V is equals to 4 by 3 pi into 125. V is similarly to 523.6 units cube. This confirms our derivation. Now let us understand why spherical coordinates are preferred. The advantages of spherical method are uses symmetry effectively, provides simplified limits, allows faster computation. Because of these advantages, spherical coordinates are ideal for spheres. Now, let us move to the conclusion. To conclude, we used triple integrals to derive the volume of a sphere. We saw that the spherical coordinates are the best choice for this problem. Finally, the derived result matches the classical formula, proving the correctness of the method. Now, I hope everyone enjoyed this session and understood what I have taught. Thank you.